bitch the fuck. I might do mine upstairs because I don't think I'm going to listen to it in the back.
All right, it's time. Questions from homework? Aaron?
3.3, number 8.
3.3, number 8. Fx equals this. Great. Okay. The question is asking you to find the derivative of this. Okay. Now you know, doing the rule is not hard. Memorizing the formula is not hard. The harder part is recognizing what you're dealing with. Okay. So before we even do it, let's plan ahead. What do you have here? How many functions do you have? You have 3. X, e to the x, cosecant x. Do you know the derivative of each? Yes. X, 1, e to the x, cosecant x. That's going to be negative cosecant times cotangent. So I know all of them. How will they put together? Product. Okay, so now it's settled. We have the production of 3 functions. We should use the product rule. Moreover, we should use the generalized product rule with 3 terms. So before I do anything about it, I already know what I should be doing. I should have 3 terms. For each term, I take the derivative of 1, keep the other 2. Okay, so x prime, that's 1. Keep the other 2. Now it's my turn to do e to the x. Keep the other 2. Now keep these 2 and do the derivative of cosecant. Together, this is already a good enough answer. Of course, if you want to simplify a little bit, which you don't have to, by the way, but for web work, if you simplify it, it's easier. So you don't have to times e to the x cosecant x for 3 times. Something is wrong. There's x. All right. Looks good. Other questions? All right. Oh no, Aaron.
For the writing project for number 1, where do we find the references that we have to compare to?
Google, number 1. If you can find some free resource on Google, good. Number 2, Murphy Library. Have you guys used a lot of the library resource before? If not, you can actually go there and type in all the books or articles you wanna look at. Okay, they either have a physical copy, for most of the cases, of course, or they can actually give you online access. Okay, to some of them. I would say for this case, during this pandemic period, don't try to get a physical copy. Try to make it online. Okay. For the 4, you only need 1 of them. And according to what I know, some of the teams have already found at least 1, so it's doable. Cool. By the way, the library is amazing. I mean, I read probably more than 30 books already from the Murphy Library. I never went to the library during my PhD because I prefer to buy my own books, but turns out it saves a lot of money. So you better use it. And you already paid for it, actually, so. Other questions regarding homework, writing projects? Nick?
So you only need 1 source for that first writing assignment?
Mm-hmm.
Okay, and then if we did go to Google or something like that, do you want that cited?
As you proceed further, if you're like a sophomore or junior you definitely need to cite that thing. Since a lot of people in our class just came from high school, it's okay if you don't cite it. But since you already mentioned it, you better cite it, right? That's a really good training for you. So yeah. The reason I didn't make the writing project such a big requirement is because number one, it's a lot. And number two, you guys are not familiar with how to write college papers or how to write college reports yet. Okay, that's why I say, hey, I want to save the hustle by teaching you how to write, which is going to be a huge amount of work. Okay, but if you already noticed something about professional writing, you definitely should apply that to your writing. Okay, Nick Peterson.
So yeah, I looked up one of the, I found one of the resources on Google, and I tried to read through it, and it was like super confusing. So like I just kind of looked up Fermat's method, and I had found like an article that wasn't on the resource list. Is that okay?
Technically, you should follow the requirement, but I would say like as long as you read one thing and I mean, they were asking about Barrow's method or Fermat's method, right? As long as you can comment on that method, I don't really care.
All right, sounds good.
Yeah. Keep in mind that the writing project is not for me. Okay, as long as you learned, I'm going to give you a full score. I'm not going to say, hey, you didn't do the thing I wanted to be done, so I'm going to minus anything. For Calculus 1, the writing project is basically give you something harder than a normal homework for you to spend like maybe 1 or 2 hours on to think deeper about a certain concept. So as long as you do the deeper thinking, I am okay with any kind of format. Okay, just keep in mind that's the goal of the writing project. Okay, so I don't want you guys to spend too much time on how to make that thing, how to say, meet my goal to be super rigid. So if you have any other ways of doing the writing project, you can propose it to me, and I'm pretty flexible on that. Other questions? If you find the writing project fun, you should really think about taking more math class. Okay, if you find it a torture, then do the minimum. Okay, at least do some of the deeper level thinking. Yeah, but I really think that's some good place to start to get a feeling of, you know, how to think deeply about something, because everything you guys have so far in college or maybe later is going to be a lecture-based class. And frankly speaking, we are just teaching the minimum. Anything interesting, anything that is deeper, it's actually your own job, because the instructor cannot go too deep, since not all the students actually cares about it to that level. So read more. Okay, that's definitely encouragement, not just for my class, for anything that you're interested in. Okay, read more, do better, do more than the class required, especially if that's something you want to do later in your life. Okay, you better become an expert, and you cannot expect the professor to push you to do that. You should do that yourself. Okay, I'm constantly amazed by how many people, you know, they're so motivated, and even if they just graduated from high school, but they know a lot about black hole, you know, physics or maybe chemistry or biology, way better than what I know. That's something we would like to see. Okay. All right. Other questions? Since I'm already mentioning it, if you guys have any, how to say, deep interest in some kind of thing you read a lot, definitely reach out to the professor and see if there's any way they can recommend you to do more reading, okay, to talk with you about your ideas, and also if they can offer an opportunity or they can direct you to some opportunities to do some undergraduate research. If you like something, for example, you like biology or chemistry, you shouldn't wait until you graduate to try something hardcore, right? You can actually start right now. So if you're interested in something, you know firmly what you want to do or you want to try things, talk to your professors, okay? They're super helpful. All right, let's continue with what we had for 3.5, implicit differentiation. Okay, explicit, implicit. You have everything in your notes. Just a quick reminder to give you some examples. This is explicit. Y equals a function of x. This is explicit. Oh, this is implicit, where your y is technically a function of x, but there's no way you can write it in a nice format like this. You cannot solve for y from this. Now what we want to do is we want to take the differentiation of this. The details are in your notes. We just want to quickly mention how to think about this. Well, number one, you take derivative on both sides. Number two, when you do that, what's going to happen? Well, two things can happen. The first one is about the term looking like x. It's just easy. Take it as a derivative. The second thing is going to be something with respect to y. So what you do is you should take it pretending it's x, but then you realize, oh, wait a second, this is y. Then when I finish, I better times y prime according to the chain rule. Good so far? You do the same process for every single term you have. You are going to end up with something, and you are going to end up with something with y prime there. So you have two types of terms, the terms with y prime and the terms without y prime. Now, in order to find y prime, you just move all the y prime on one side, factor it out, and then divide. This is basically what implicit differentiation is. Sounds good? All right, with that in mind, like I promised, let's try some examples. Let's still do this one together. Okay. Every single rule still apply. On the left, derivative. Then by the chain rule times the derivative of the inside. On the right, derivative of e to the x is e to the x. By the chain rule times the derivative of the inside. Okay. The derivative of x plus y. Well, the derivative of x is 1. The derivative of y is just y prime. Like we mentioned last time, x and y are both function of x. So technically we have a product rule here. And x prime give you 1. Up to now, all the derivative is done except for y prime, and you cannot do any further because you don't know what y is. So just keep y prime there. Now, like I said, clean the terms by FOIL everything out for you to recognize who has a y prime and who doesn't. Move the y primes together. Everything else together. And the reason you put them together is you want to factor them out and finally divide. Does everything look all right? Cool. If you need more time on reading the steps, keep going. If you're already good, try this example yourself. Find the equation of the tangent line. Y sine 2x equals x cosine 2y at pi over 2 pi over 4. All right. Any questions? Anton.
Okay, so I still don't entirely get where you get the y prime in the beginning of the equation. Because aren't you just doing the product rule instead of the chain rule?
This, right?
Yes.
Okay. That is going to be y prime sine 2x plus y sine 2x prime. That's exactly the product rule.
Oh.
Right?
Yes, yes.
Yeah. So, and then what I did is actually I took this prime and expanded to be cosine 2x times 2. But really, so the y prime come from product rule. You're right. The sad thing is after that, I have to keep it that way because there's no way I can do anything further. So that's where this one comes from.
Oh, okay.
Yeah.
I think that makes sense.
Cool. Yeah, anything other than y, you can take the derivative. But if it's just y itself, you take the derivative, it becomes y prime. And that's what we're looking for. So there's no way you can simplify. Just keep it there. Are we good on this one? All right. If you're okay with this, I think you can already follow the implicit differentiation. Now what you need is just a little bit more exercise, which I would say like go to the homework. And it may be challenging because we're trying to, how to say, condense everything you had before, chain rule, product rule, quotient rule, together with implicit differentiation. Okay. So if you have trouble there, bring them to class. I'm more than happy to answer. If you have 10 of them, I would rather to answer all the 10 of them. Okay. That's almost like we did 10 more examples together. So try it in your homework and bring the questions to class. Now, just a quick heads up. It's pretty amazing what we just did. We just find the derivative. Does it work? Well, we can type it in Desmos and see what kind of graph do we have here. And this is a really, I won't say weird, but this is really interesting graph. Okay. And we don't even know how to draw it, but somehow we were able to find the derivative at pi over 2, pi over 4, which is here. Okay. And if we type in the tangent line, we just find okay. Seems like we did a pretty decent job. And that is the changing rate. Okay, from here you can see, well, with all the methods we just did, I think we're pretty confident to say we're doing it in the right way. Okay, even for something as complicated as this, even though we don't know what the graph looks like, we can still go ahead and try to find the derivative. By the way, is this one even a function, the red lines? Not really. It doesn't pass the vertical line test, right? That's why we call it implicit, because implicit can cover so much more, can cover something which is not even a function. Okay. Implicit also treat x and y equally. They don't say y is more important than x or x is more important than y, because barely speaking, you guys are the same. Okay. Good. Oh, by the way, I forgot to show. Do you remember the thing we did last time with all the design of the thing like this? Okay, we try to say, hey, we got nice patterns here, 3, 4, and eventually if we put 10 here, we got something which looks really nice. Okay, now Do we observe those kind of things in real life? The answer is definitely yes. It's not here. And I need to find it in my notes. Let me see, which one is it? Yeah, I would say this one. All right, you can actually Google this one later by yourself, but I think you get what we mean by that. Now the interesting part is we can actually reproduce all those kind of graphs easily with this former. Okay, so the question becomes why? Okay, how do you calculate all the hertz, the frequencies people need in order to produce those kind of patterns? All these things actually is hidden in mathematics. Okay, as long as you know how to solve this equation, you will be able to reproduce that thing. Moreover, before what we saw is a square close, right? What if that thing become a circle? What if that thing become a triangle? The pattern will change. But how will the pattern change? Again, you solve an equation by setting a different parameter. You will be able to reproduce them all. Okay. That's something called nodal line. If you want to Google it, feel free. I'm going to type in the channel. Nodal line. Okay. It's actually pretty amazing. And you can do it actually at your home. If you just find a drum with some salt, you put something on it and you just speak to it at a frequency, just make it stable, like things like that. You will see those patterns yourself. You can change the pitch and try to see when the patterns start to show up. Okay, but that's just for fun. All right. Do we need more examples on implicit differentiation? If yes, click yes. Otherwise, we will move on. Oh, we still need more. Okay. Try this one yourself. x. Let's try y over x. Okay. We're open for questions. And if you could do this, you're way beyond what's required by the exam. This will be harder than what the exam will be.
How'd you get the secant squared y over x, like from step 2 to 3?
Can you see that? I basically splitted the two terms, the one with y prime and the one with not y prime, by dividing x squared. So I got y prime times x divided by x squared. That's going to be y prime divided by x times secant squared y over x. So that's what happened here.
Okay.
Who asked it?
Nathan.
Nathan? Okay. Do you get it?
Yeah, I got it now. Thanks.
Yeah, I skipped some of the steps to save some room. And it's really, a pain in the butt to copy all the stuff. All right. Even if the thing is long, we have a quotient rule, which is a lot of work, fractions, splitting, whatever. But just follow the procedure and trust the formulas. Okay? Don't try to rush things through. Do one thing at a time. Eventually, you'll find it's just term with y prime and term without y prime, no matter how complicated it looks. Then we just copy and divide. No big deal. All right. Are we good on this one? Cool. You can create some problems by yourself. And also, I would personally suggest try the harder ones in the textbook. If you're okay with the harder ones, that means you have to be okay with all the rules. Otherwise, there's no way you can just get it by lucky guess. Okay? That's why I want everybody to try the harder ones. And if you can do the harder ones, the easy ones, you come back and look at it, you find, wow, this is really easy because now I see the structure. Okay, so try the harder ones. I know it can be time consuming, but if you spend 40 minutes on a harder one, it's way better than spend 10 minutes each on 4 easier ones. Try the harder ones. In the textbook, which means the ones probably have a big index, like 40 something or 50 something. Okay, that's it. That's implicit differentiation. Now with that in mind, what we can do now is we can finally finish our table. We can do log, okay, and we can do trig inverse. After that, the whole table is done. Let's do log first. Trig inverse, we have 6 answers. Okay, let's start with E. And then we look for what is the derivative of ln x. Like we said, ln x and e to the x, they are inverse function to each other. So definitely to get the derivative of the e, I should get it from the derivative of e to the x. Somehow this factor need to show somewhere. Okay, good. Now let's take a look. Let me reformulate what we have here. We know y equals ln x. We want to find y prime. That's our goal. But we're not familiar with ln. We're more familiar with e. And then we realize this is the same as saying x equal to y because they are inverse function to each other. Still okay? Now, instead of finding y prime here, how about I find y prime here? Because they're the same thing. Okay, but if I find y prime here, I can use the derivative of v. That's the beauty. But now you realize to do that, I have to do implicit differentiation. Simply because your y is not a function of x anymore. It's in an equation. But it's doable. It's actually easier than anything we have done before. Sounds good? Derivative on both sides. What's the derivative of x? That is 1. What is the derivative of e to the y? That's going to be e to the x, if it's x. But if it's y, I do this. When I finish, I times y prime. Sounds good? Finally, what is y prime? Exactly how we solve it. 1 over e to the y. Technically, this is already a good enough answer. But for formulas, of course, we want to change it to x to make it look nicer. And then we realize, actually, e to the y is just x. So that's a nice and clean formula. And how do we get it? We get it from e by doing the inverse. Okay. But of course, e is to the y, so we times y prime. We solve the implicit differentiation. Sounds good? We can go ahead and do all the rest. What about a to the x? If you take log a, something other than e, you can quickly do it yourself. I'm just going to skip it. It's going to be 1 over x, but then times ln a. This definitely comes from this. Okay. Try to do it by yourself. It will be very similar to what we just did for ln, but now this works for any base. Okay. Second, trig. Trig inverse, actually. Okay, same trick. Well, let y equal sine inverse x. We want y prime. Then we say, well, it's the same as saying x equals sine y. Find y prime. Implicit differentiation, 1. Cosine y, okay, times y prime. Sounds good? Okay, again, once you transform it, you got exactly the other one. For sine, inverse, don't do it. Let's do sine instead, okay? But to do that, you switch x and y, you have implicit. Now for trig, there is something in addition that is change to x. We want something in terms of x, not in terms of y, if possible. Now you need to ask yourself, what do you know about x? Well, x is sine y. What do you have in the formula? In the formula, you have cosine y. Still okay? What you want is you want to represent cosine y in terms of x. That means you want to represent cosine y in terms of sine y. Can you represent cosine in terms of sine? The answer is definitely yes. It comes from trig identity. square root. Okay. Plus or minus. Okay. That means y prime is going to be 1 over plus or minus square root of 1 minus sine square y is nothing but x squared. That's already a nice looking formula with only x. Okay. Now, you need to go ahead and try to think more. Does it mean that I have two possible changing rate? What does it even mean? That means starting from here, I may go up and down at the same time. How am I supposed to draw the graph? Like that? From here, you can see it's not differentiable. So this is definitely not a good answer. We only need to have one. Okay. So which one? Now you need to go back to the definition. When you write this thing down, maybe you recall, maybe you don't. You have a hidden assumption that is y is in that's how we define the sine inverse. And with that in mind, what do you think cosine y will be? It's going to be positive no matter which quadrant you're in. You only have two options. They both give you positive. So we can finally say this is this. Due to the fact we do have a restriction on our y by definition of sine inverse. So to summarize, that's what we have. It's too small. Sounds good. For cosine, you can repeat the same thing. For tangent, you can repeat the same thing. For tangent inverse, you just change it to be tangent. Once you change it to be tangent, you'll know the derivative. The only difficulty is when you finish, you have to change everything back to x. And to do that, you need trig identity. Nothing more than trig identity. Is the logic clear? We will do all the 5 next time. Okay, that's all for today.